Hi everyone, welcome to this class where we are going to study about the PN junction and diode. This is a very important topic and the application of the semiconductor with the help of the diode. So let's take a look, and I'm going to make these physics concepts absolutely easy for you. So keep your pen and paper ready and let's begin. Before we begin, just a quick reminder, do check out the courses on our website manochaacademy.com and our Android app Manocha Academy. All the links are given below. And please do share it out with your friends as well. So what is the difference between a conductor and a diode? So we'll be learning about diode today. All of you know what is a conductor? Conductor, like if you take a copper wire or a metal wire like this. Now if you connect it to a cell, to a potential. So for example, if I connect it like this to a cell or a battery, in which direction can you guys tell me will the current flow? You'll say, sir, very simple, from positive to negative. Okay, so very easy. We know the direction again of conventional current will be this way. So direction in the conductor will be this way. Now suppose we reverse the battery and I connect it to you like this with the battery reversed. Okay, so there you guys, you can see the battery has been reversed. Now tell me what will be the direction of the current. Tell me in the comments. The direction of the current will be reversed. Okay. The conventional current flow from positive to negative and this way. So you can see conductor has no preference. It can allow the current in this direction or this direction depending on your the cell, the potential difference, right? Which side is positive or negative. But diode is a very special device because it allows the flow of current in one direction. Okay, so diode is very interesting. Because suppose, and this is how we represent, this is the symbol of a diode which we'll be talking in detail. So just take that, that's the symbol of a diode, and let's say I connect it like this. Okay, let's say I connected like this, and this will be called the PN diode, we'll see. So P side I connect to positive and N side to negative, which we'll look at the details. The current will flow in this direction. So diode will say no problem, I allow the current to flow. But now when you reverse the battery, that means positive guy on this side and negative on this side. In this case, the diode is not like the conductor, it will not allow the current to flow. So here the current will not be allowed to flow, or practically there will be a very small current. Okay. So when I was saying not allowed, I was lying. Okay, but that's a simplification, right? So you can say very small current or no or very small current. So clearly you guys can see the difference between a conductor and a diode. Conductor allows in both directions. Diode allows current to flow only in one direction. But what is a diode? That's what we are going to learn about. So in the last class, we have discussed the different types of semiconductors. You had the intrinsic semiconductors, but the more useful ones are the extrinsic semiconductors, right? And we talked about the N-type and the P-type. There are two types of semiconductors, right, which we are going to be using today. So if you missed that video, please do watch that, right? So remember, if you do this if you take silicon atoms and if you dope it with phosphorus, silicon has valency of 4. It has 4 electrons in the valence shell. Phosphorus is pentavalent, 5 electrons in the valence shell. So there is basically extra electron here. So there is an excess of the electron. Can you see? There will be extra electron. And this type of doping, like we learned in the last class, gives you a basically N-type semiconductor. N-type because electrons are negative. Not that the semiconductor is negative, but electrons are going to be your major charge carriers. So it is N-type semiconductor. On the other hand, if you take your same silicon crystal, pure silicon crystal, and dope it. Dope means adding an impurity of, let's say, boron. Boron is trivalent. It has only 3 electrons in the valence shell. So here you can see there is a deficit of electron, or we can see that basically a hole will be created, right? It cannot share with the neighbor. So hole is created, and hole, so electron is negatively charged, hole is positively charged, which is basically the absence of an electron, right? You can say no electron there, so positive charge, and that is why this is called P-type doping. So all this N-type, P-type doping and this I have discussed in the last class. Why you'll see this is important? Because we are going to be learning about PN junction. What is the meaning of PN junction? So imagine like this. Let's say you take a slab of pure silicon. Okay. And so like this is your slab of pure silicon. Imagine initially this is just pure silicon. And now what you guys do, on this side you dope with a trivalent. Okay, so you dope with something trivalent like boron, right? Boron doping, it's written here. So this side will give you a which type of semiconductor? Tell me. On this side, if you dope with boron, so on this side basically you will get a P-type semiconductor. Do you guys agree? What is the meaning of you will get a P-type semiconductor? Means there will be excess of holes, right? And holes we represent as positive charges. So you can say that the entire thing is neutral, but there is an excess of holes. So this is how usually you'll see in the book diagrams they have represented the P-type semiconductor. So we have done trivalent doping on this side, creating an excess of holes. Is that clear? Creating an excess of holes. On this side, so same silicon crystal, on this side you do pentavalent doping, the opposite. So you put something like phosphorus over here. So clearly you will have an excess of electrons. Clearly you will have an excess of electrons. Yes or no? Students, tell me. Is that clear? You will have an excess of electrons. So what side does this become? This becomes your N side. This becomes your, so pure silicon is no longer there. This becomes your N type. So it is not like you are taking a P type and N type and making a nice beautiful sandwich which you are going to eat. No. In that same silicon crystal, on one side you are doing trivalent doping, another side pentavalent, hence creating a PN and a PN thing over here, right? A PN mixture you can say, or we call it a PN junction, right? Junction means what is in between. So if you look on this side, it's P type. If you look on this side, it is N type. Is that clear? Okay. Now one question is, we have learnt, so these are clearly what I have marked over here, the majority charge carriers. The majority charge carriers. But remember, we have discussed last time that on the P type, there will still be some electrons. There will be few electrons. And those few electrons are basically thermally generated, right? Due to the breaking of those covalent bonds. So there will be few electrons, but majority charge carriers are holes. Okay. So what I have represented with these plus things. So here you can write holes are the majority charge carriers and electrons are few. Please make these notes. If you understand these concepts, I am going to explain you each and every concept and I am sure the topic will be crystal clear. Okay, like silicon crystal clear. So this holes is in majority, here electrons are minority, few, right? Or we can even put the word minority. What about on this side, guys? What about on the this side? This side clearly you can see it is opposite. So this side it is opposite. The electrons are in majority, and there will be a few holes also which are thermally generated, right? Like we discussed. So there will be few holes. Holes we represent with the plus. So holes are in minority. So when you have this situation, this is called a PN junction. But you'll say, what's the big deal? What's the big deal of the PN junction? Well, this is the making of your diode, right? The diode that we talked about, a device. So diode is basically a device which allows current to flow only in one direction. The other direction it hardly allows. It says stop. I don't like current in this direction, right? So that is made using a PN junction. And we'll see that how, right? So first let's see what happens when you do this. So when you create a PN junction like this, what's going to happen? So remember here, again quickly mark on this P side, this is the PN junction. So I'll write PN. On the P side, you have the majority of the holes. Holes are in majority. Okay. Right now I'm not showing the electrons. And here electrons are in majority. Now note, as we discussed, this is one silicon crystal. So there is no blockage over here, right? There is no blockage over here. So what do you think is going to happen if there the holes are in majority here. By the law of nature, or the process called diffusion, just like there is diffusion of gas, diffusion of perfume, diffusion of food from the smell of the food of the kitchen, from the kitchen. Same way over here, there will be diffusion of holes from high concentration to low concentration. Yes or no? There is going to be diffusion of holes from P to N side. Similarly, there will be diffusion of electrons, the majority guys, from N to P side. Do you guys agree? So what is going to happen? There is going to be this diffusion of holes and electrons. So we can say these holes will start moving to the P side and these electrons will start moving to the N side. Okay. So as a result, what will happen? When these holes move to the P side, hole is basically what? A positive charge. Holes are this positive charge. It's actually basically the electron gap which is moving, right? The electron gap. Now, hole is basically the absence of the electron or a positive charge. So if I take away some positive, or it happens on its own, diffusion, if it happens, then what will be left on the left side, on the P side? Tell me, what will be left? There will be negative over there, and on this side, positive will be there. Yes or no? Do you guys agree? So what will happen is, so imagine these holes are diffusing, and especially the holes and electrons near the junction, right? It's not like all the holes will move or all the electrons will move. So the ones near the junction are diffusing. So you can imagine that what will happen as a result of this diffusion, a negative charge will start getting developed because positive guys have left. Same way, when the electrons start diffusing from this side, a positive charge will start getting developed. Yes or no? And be very careful, a negative charge develops on the P side. Don't say P, I'll put positive, right? Because holes are moving, negative developed on the P side, positive developed on the N side. And now another question is, why is the positive and negative developed? Why is that charge not moving? Because that is immobile, right? Remember the strong covalent bonding? In silicon? So only that extra electrons, it's easy to think of electrons, right? Electrons moving or the holes moving, right? So they are able to move, but not the other immobile ions. So that is why a charge develops. So charge is due to immobile ions. And so this layer of charge, what is formed is known as your depletion layer, because it happens due to charge depletion. Depletion means loss, right? Charge loss happens. Is that clear? And this diffusion is happening, so that is creating a depletion layer. And this diffusion of holes and electrons is known as diffusion current. So you write down this important word also. So the diffusion that is happening on either side, because it is the movement of charge. And what is movement of charge? You know from physics, right? You know in physics it is a current. So therefore you are having a diffusion current on both sides, right? So because this is from positive to negative, and obviously if negative moves here, negative to positive, so it's in the same direction, it's not cancelling each other. So in summary, what we learned, that from the P side to the N side, because of the diffusion of holes and electrons, you get what is formed as your depletion layer. Very, very important. Is that clear? So your depletion layer is formed around the PN junction, right? So we can usually see in your books it is marked like this. So on the P side, what was developed? Negative charge. So let's mark negative here. On the P side, or I'll mark in white color. On the P side, what was developed? Negative charge. What was developed in the positive side? On the negative side, positive charge. I shouldn't say negative side, positive side. Sorry, my mistake. P-type N. Okay? It's a PN junction. So on the P side, negative charge. On the N side, positive charge. And this layer, this is formed. Okay? This layer, this is formed because here they are all holes. and a few electrons in minority. Here they are all excess electrons. So this layer which is produced is called your depletion layer. Now can you guys guess how thick is the depletion layer? Is it very thin or very thick? What do you think? So depletion layer is actually very thin. It is a very thin layer. What is the size? Very thin, of the order of 0.1 micrometer to 1 micrometer. That's it. So don't think it's one big fat layer. It's a thin layer formed around this PN junction. Now if you have this kind of charge developed here, positive here, negative here, right? Note that this is not the positive negative charge. These are the holes and electrons, because this part of the crystal is neutral, right? It is here where the charge is developed due to the movement. Okay, so this positive negative is your depletion layer, and when you have positive to negative, if you have positive one side and negative one side, what are you having effectively? It's a cell, right? Or it's a battery, or we can say it's a potential difference. Yes or no? So many times you'll see that this will basically, this is a potential difference from positive to negative. So many times you'll see this is shown like this with a fake battery. So this is not a real battery. Please don't think I've connected a real battery here. No, because this side is positive, negative. So basically this is a potential difference, or you can say that there is an electric field. Yes or no? So we can say that there is an electric field from the positive to the negative side. Potential difference, electric field, whatever you want to call it. So both concepts are clear, that in this depletion layer there is an electric field from positive to negative, or we can say there is a potential difference which I have represented by this fake battery. Okay, so please remember, this is not a real battery that we have connected, it's a fake, just to represent the layer. Next, let's talk about the concept of barrier potential. So remember, we talked about the potential. Potential is developed where? Across the depletion layer. So this is your PN type, P type and N type, and this was your depletion layer. Okay, so we can say a potential difference is developed here. Now why is it called a barrier potential? Let's take a look. So we know that this depletion layer was created by the movement of the holes, by the diffusion. Remember the diffusion current word? It was created by the diffusion of the holes. Now what do you think this barrier potential is going to do? Because it is from positive on this side, remember, with this fake battery, you can draw it with this dotted thing to show it is fake. So this positive potential, will it allow the holes to come here or push them away? Positive repel. So this positive potential which is developed due to the movement of holes, it starts blocking them, right? It starts blocking them. Same way you can see that the negative charge, right, that the electrons here, right, when they moved over there, this barrier potential is again going to push them away, because negative repel each other. So they are actually pushing them away, because these are trying to move this way, but it is blocking it. So that is why this potential difference is called a barrier. Barrier means it is blocking it. Okay, so this electric potential, right, developed across the depletion layer, what does it do? It is pushing the holes on the P side and the electrons on the N side. So can I say in one word, it is pushing the majority charge carriers, right? So it pushes away majority charge carriers, or basically you can say it blocks the majority charge carriers from further diffusing. Yes, so that is the job of your barrier, basically your barrier potential. Is that clear? Now question is, what is the value of this barrier potential? What is the value of this barrier potential which I have represented by this fake battery? So we can say for silicon they have measured the barrier potential is approximately 0.7 volts, and for germanium it is 0.3 volts. Okay, so reasonably decent potential, barrier potential is developed across this PN junction. Now we have learnt about diffusion current. Remember, diffusion current was the diffusion of holes from the P side and electrons from the N side. But now let's talk about the concept of drift current, which is again related to the barrier potential. So what is barrier potential doing? Barrier potential is positive, negative here. This is your barrier potential. Now, we said that it is pushing away the holes from this side, right? But remember, I said holes are in majority. There are a few electrons which are in minority, right? So here I am going to represent the minority charge carriers. Electrons are also there. Of course, there are lots of holes. Holes are in majority, but electrons are in minority. So this electrons will get pulled by the positive. Yes, electrons will get pulled to that side by the positive potential. Same story you can apply on the N type also. Here holes are in minority. So holes are in minority. Your electrons were in majority. So these will again get pulled. The holes will get pulled by the barrier potential, which is negative on this side, right? So it is trying to pull these holes. So do you guys agree that what is the barrier potential doing? It is opposing, I repeat, the majority charge carriers. Understand, very simple. Barrier potential opposes majority charge carriers, but it pulls the minority charge carriers. And when there is pull or movement, there will be current. Okay. So drift current, please write, it is the movement of minority charge carriers due to the barrier potential. Does that make sense? Now, is this drift current going to be very large? No, because it is the pull of the minority charge carriers, right? They are smaller in number, right? So you can imagine the drift current will be small, but clearly there will be a current. So this is what is interesting and tricky in semiconductors, that we may think about the majority, but don't forget the minority also. So you have to consider both cases. And this guy is called drift current. Drift current. Drift current. Clear? So what are the two currents that we learned? Diffusion current and drift current. So what is the relation between them? So it's very interesting. So when the story starts, right, when you are creating the PN junction, then the diffusion will start happening. Think about it. So when you create the PN junction, the diffusion will happen, right? That's when the diffusion happens. So that means when the diffusion is happening, so that means the diffusion current is high, right? So we can say in the start, the diffusion current is high because the diffusion has started happening, right? So that was the story, that the majority charge carriers start diffusing, right? That will cause your diffusion current. And later, so what does that do? Same way here, majority charge carriers are diffusing. So right now there is no drift current. That builds up the barrier potential which will create the drift current, right? So this diffusion will build up this barrier potential which will create the drift current. Okay, so initially there is only diffusion current. So diffusion current is initially high. That builds up the barrier potential, which so that builds up the depletion layer, which builds up the barrier potential, which will create this drift current, because drift current is this one. So please be clear. So let's mark it clearly. This side is the diffusion current. We are showing again the conventional direction from positive to negative. And here will be the drift current. Again, I am showing the conventional direction. So as the depletion layer grows stronger, the drift current will start increasing. So if you are having diffusion current happening this way, drift current happening this way, initially this guy is high, later on this one becomes high. So as you can guess, there will come a stage when both are equal. And when both are equal, what do we call it? That's right, we call it equilibrium. So at equilibrium, right, so in starting this is high and this one we can say, later this increases. So finally we reach a equilibrium state. So at equilibrium, your diffusion current is equal to your drift current. Do you guys agree? So at equilibrium, see, both currents are actually happening, but they are sort of cancelling each other. So what will you remember in summary? There are two very important currents. Diffusion current, by the word you can understand, it is due to the diffusion of the majority charge carriers. And drift current is happening due to the movement of the minority charge carriers. Is that clear? So in summary, our PN junction diode, the PN junction looks like this, which is basically our which is going to act like a diode, right? And we'll see why. How will this magical device or this magic here, just by doing this different type of doping, create a diode? Diode means a device which allows current in one direction. And so finally you will see this is the overall picture. Please look at it carefully. On this side, what can you see? This is the P type. So here clearly you can see, in summary, holes are in majority. Holes are in majority. Electrons are in minority. Electrons are in minority. On the N side, the story is opposite. The electrons are in majority. And your holes are in minority. And remember, what was this developed over here? This was called the depletion layer, which is due to the immobile charges, right? So movement of the electrons left a positive charge here, movement of the holes left a negative charge here, creating this depletion layer, okay? And you had that where the drift current was balancing the diffusion current. So this is your overall story, and again remember, this is just a fake, again I remind you, this is a fake battery representing your barrier potential. So this is representing your barrier potential. Okay. So basically barrier potential is preventing the further movement of the majority charge carriers, right? Pushing them away. Same way pushes the electrons away here. Now let's see, to understand that how does this structure or this magic P-type plus N-type behave like a diode, let's actually connect it to a real cell or a battery. And again, see, I'm making your concepts clear. Please, this is your fake battery, fake, right? If you want, I can again draw it with a dashed line. So this is not your real battery which I'm connecting. So please, some students think this is the battery. No, we are going to add an external battery. We still haven't added it. This is just the original guy, original PN junction. Now what we are going to do is, we are going to connect the external battery to it, right? So this time what do you do? This is your P side, this is your N side, remember? P side, N side. If you connect the positive of the cell, if you connect the positive side of your cell or battery to the P type, and you connect the negative to the N type, very easy to remember. So this type of biasing is called forward biasing. Okay, so this type of biasing is called your forward biasing. Because diode has two terminals, right? So why it is called a, oh, so I forgot to mention why it is called a diode. It has two sides. Di means two terminals. Okay. So if you connect the P terminal, means there will be a contact point here. So if you connect it to the positive side of your cell and the negative side of the cell to the N type, this is called forward biasing. Now if you do the opposite, if you connect the positive side of the cell to your N type and the negative side of the cell to your P type, then this thing is called reverse biasing. This is called reverse biasing. And this PN junction, remember, we used to symbolize as a diode. So rather than every time drawing this, we will simply represent it like this. So how will you show your forward biasing? So this side, or we can write these words here in the middle. Your forward biasing will basically be represented like this, because this is your P, this is your N. So in diode symbol, the triangle is P, the line is N. Okay, this is your P, this is your N. So reverse biasing automatically becomes like this. Clear? So this case is your reverse biasing. And now we want to see one interesting thing, like we learned that current is mainly allowed in which direction? In the forward direction, right? So here is where there will be current, and here there will be hardly or negligible current. Same way here, current which will flow from positive to negative, here negligible current. So first let's talk about the forward biasing and see why there is current. Okay, so forward biasing means now we are connecting our external battery, right? So we have got our PN junction or our diode, and this time we are connecting our external cell or battery like this. Okay, so everybody has connected it, and this is your barrier potential. This we can represent as barrier potential as VB, and this one as the external one is V. Okay, so now what's going to happen over here? You can see that this is the positive potential. So what is positive potential going to do? This is positive potential, that means this side is positive. Positive potential is going to push the holes, because positive repel, so it's going to push the holes from the P type and send them to the N type. Do you guys agree? It is going to push the holes. So here you can see that the holes will get a pushed. Yes. So the majority charge carriers get a push from which are the holes from the P side. What about the N side? N side, this is negative, so this is negative. So negative repel. So here the electrons, which are the majority charge carriers, they will be pushed from the negative side. Where? Towards the depletion layer. So if you guys imagine this, visualize this. From this side the holes are being pushed, from this side the electrons are being pushed. So it is getting sandwiched from both sides. So now you think and tell me, will this depletion layer increase or decrease? If this side is getting a push this way and the holes are getting a push this way, the electrons are getting a push this way, will the depletion layer increase or decrease? The answer is very obvious, it will decrease. So this is very important. The depletion layer decreases. Note that down. Depletion layer, that is the width of the depletion layer, decreases. Very important. So what is happening over here? We clearly saw that there is going to be a decrease in the depletion layer. And now actually why is it decreasing? Basically you can think that these holes which are being pushed, they will go and neutralize these negative immobile ions, because these fellows can't move, poor fellows, these can't move. But holes which are being pushed here, so these plus will go and cancel the minus over here. So that is why it is sort of breaking down, decreasing the depletion layer. Same way the electrons here are being pushed onto this plus, and they are breaking down this depletion layer. So the width of the depletion layer will slowly decrease. Yes. So this is what is forward biasing. It is creating this effect, right? Depletion layer decreasing because positive are cancelling the positive are going to cancel these negative will get cancelled by these positive. Now as you can see that this external potential, this is the external one, is that opposing the barrier potential or favoring it? Clearly you can see that this side is positive negative and this one is positive negative, so they are opposite of each other. So clearly we can see that the external potential that we have applied is opposing the barrier potential, right? The barrier potential is getting opposed. So barrier potential getting opposed means barrier potential decreasing. So we can write this, just like depletion layer decreasing, barrier potential decreases. And remember, barrier potential for silicon was 0.7 volts, for germanium 0.3 volts. So if that barrier potential gets less, that means more, because what was barrier potential doing? Its job is to act as a barrier to the majority charge carriers, right? It was pushing away the holes, pushing away the electrons this side. So if the barrier potential decreases, the blockage decreases, that means the conductivity increases or resistance decreases. Yes or no? Very important concept. If the barrier potential decreases, therefore we can say that resistance decreases. So that means this PN junction will favor the current this way, right? So the current will flow this way because the barrier is decreasing, so allows for the flow of current. So that's what's happening, that resistance decreases and the current will flow, and this current is due to the majority charge carriers. The current is the flow of the majority charge carriers, right? Because this is positive, So this external positive will be pushing the holes, right? So current is due to the majority charge carriers, which you can see obviously because this plus is pushing the holes. Now the barrier has decreased, so holes are excitedly going that way. This minus is pushing the electrons, the barrier is decreased, broken down, right? Not absolutely zero, but decreased, right? So see, you can see the flow of current. And again, conventional. Holes this side means electron movement, this side means positive charge movement this side, right? So they are not cancelling each other. The effective current is this way. Effective current is this way due to the majority charge. Is the concept crystal clear? This is your forward biasing. Next, let's look at the opposite case of reverse biasing. Again, reverse of the external voltage that you apply. Okay. So this was our fake thing. This was our fake barrier potential, and now we are applying the reverse biasing. Means you're connecting the positive side to the N type, you're connecting the negative side to the P type. This is what you have ended up doing. This is your case of reverse biasing. So what will happen in this case? In this case, guys, what is going to happen? The positive end is basically going to pull the electrons. The electrons are the majority. First look at the majority case. So it is going to pull the electrons this way. Again here the negative side is going to pull the holes this way. Right? So look what's happening. The holes, the negative side is pulling the holes this way. The electrons are being pulled that way by the positive side. So electrons being pulled this way, holes being pulled this way. So what do you think is going to happen to the depletion layer? Again, look carefully. Electrons being pulled this way, negative to positive. Holes being pulled positive. Electrons this way. By mistake, I told the opposite. This side is the holes, right? Holes are being pulled this way, and electrons are being pulled this way. So clearly, you can see the width of the depletion layer increases, right? So depletion layer width, depletion layer increases, its width will increase. And now if you look at this external, V external and the V barrier, they are supporting each other. Can you see? Plus, plus, minus, minus, right? So already this was causing a barrier, right? Barrier from this side positive to negative. On top of that, you have added another blockage, another barrier by the external side. So clearly guys, the barrier potential will increase. The barrier becomes stronger because the external is supporting the barrier. In forward biasing, external was opposing it, decreasing the barrier. Okay. External is here supporting it. So if barrier increases, that means the barrier to the flow of the majority charge carriers, that means resistance will increase, right? So this increases, so resistance will definitely increase. So it becomes much higher, and that means that will oppose the flow of the majority charge carriers. So now question is, should we see zero current? But this is where PN junction or semiconductors, do not forget about the minority. Do not forget about the minority. So when resistance increases, if you think about the minority, what is going to happen here? Look carefully. Now we will not look at the majority, guys. We look at the electrons on this side. Electrons on this side are being pulled drift current by the depletion layer, and they are also being pulled by the external. So do you guys agree? The electrons are being pulled. So minority charge carriers are going to be pulled this way. Same way the holes on this side, which are the minority, are going to be pulled towards the negative side, right? So they are going to be pulled. So yes, that will be your the drift current, right? So that will happen, but basically that is since the minority is very small in number, it will be very, very small, like of the order of microamperes, right? So we can say it is approximately zero. Clear? So here one very important thing, current will flow. Current will flow. So I'll mark it with a small I, right? I will be very, very small, very low, in the order of microamperes, and it is due to minority charge carriers. So that is why if reverse biasing they tell you zero current, no, that's a lie, right? It is approximately zero, right? So therefore you can see our diode is a great device which supports or allows the flow of current on one side and opposes the flow of current in the reverse biasing side. Is the concept clear now? So here the current is due to the majority charge carriers. That's why it's a major current. You can remember like that. It's due to majority charge carriers. Yes, it's a major current. Here it is due to minority charge carriers. It's a minute current. So now let's try to combine these two and show them in a graph. We are going to combine the forward and reverse biasing and show them in a graph like this. Okay. So here what we are showing is actually called the characteristic curve of a diode, because it is showing you the full characteristic of the diode, that what is its behavior. So this is a current versus voltage graph. You can see current is on the y-axis, voltage is on the x-axis. So this side means positive voltage, this side means negative voltage. So therefore this side, if positive voltage means this is basically your forward biasing, right? So this is basically your forward biasing. So this side is your forward biasing. What about this side where there is negative voltage? This is the opposite. So this is your reverse biasing. So look at the interesting story here, that as you increase the voltage, the current increases little. Okay. So as you increase the voltage, the current increases, because here the forward biasing, right? It is current due to the majority charge carriers and it is basically opposing the barrier. Remember there was a barrier potential. It is a barrier potential that it's trying to break or oppose. So till the barrier is there, the current is small. But remember the barrier potential for silicon was 0.7 volts. Remember the barrier potential was 0.7 volts. So at 7.7 volts, the barrier breaks down, right? The barrier breaks down, and now as you increase the voltage, the current becomes quite high. Okay. So this voltage where the barrier breaks down, because till then the current was small, but then suddenly you can see exponentially like the current is rising. So this type of voltage is called your knee voltage. You can also call it cut-in voltage, or we can also call it threshold voltage. So all these different words are there for it. Knee voltage, cut-in voltage or threshold voltage, where current you can see suddenly rises. And this is for the forward biasing case. Now let's look at by the way, this current on this side is in the order of milliamperes. Okay. So you can note it down. So current on this side will be in the order of, you see in the picture in your book, it will be written in the order of milliamperes, 10 to the power minus 3 ampere, 1 by 1000th of an ampere. When you look this side, negative side, you can see that you are increasing the voltage, there is hardly any current, right? Very low current on the reverse side. So very small current. It is there, but very small. And this is in the order of microamperes, not even milli, 10 to the power minus 6 ampere. And you are decreasing the voltage, still nothing is happening. Suddenly it will also hit one voltage, special voltage called breakdown voltage, where this time this is basically what? Where there is a complete breakdown, right? Where there is a complete breakdown because you are basically opposed it and the current suddenly increases. So this voltage that we hit, where basically now the diode the diode loses its ability. It no longer behaves like a diode, it also starts giving current. So this is called your breakdown voltage. So this voltage is called your breakdown voltage. So we can talk about the resistance of a diode. What is resistance of a diode? Nothing different from a conductor. Remember what is the definition of resistance? Voltage by current, or you say change in voltage by change in current. So please write down your resistance of the diode will be your change in voltage delta V by the change in current delta I. That is called your resistance. And this is also called the dynamic resistance. Why the word dynamic? Because the resistance of the diode, you will see, let's see, is it going to be constant or not? Let's see that. So delta V by delta I, so this is basically this graph, right? We are seeing a graph of current versus voltage. We are seeing a graph here of current versus voltage. So guys, can you tell me what is the resistance will be, what part of the graph? Delta V by delta is basically the slope, right? So how will you calculate it? Basically you take 2 points like we do in physics and maths. You take 2 points on your graph and you measure your change in current here and your change in voltage. Voltage is along the x-axis, so you will measure your delta V. Current is on the y-axis, you will measure your delta I. And be careful, don't do delta I by delta V, because resistance is V by I, right? Delta V by delta I. So please substitute the correct values and you will get it. So this is basically your sort of the slope, or actually 1 by the slope, right? Because slope is delta I by delta V. But like 1 by the slope, or basically related to the slope. And can you see that the slope is changing? Can you see the slope is changing? It is not constant. So that is why it is called dynamic, because the resistance changes. Resistance of the diode is not constant. When the diode allows for conduction of current, its resistance will be low, or you can say conductance, conductivity will be high. And here it hardly allows any current. So you can clearly see the high. Where is the resistance the highest? In this curve? Clearly over here, right? Very small current, even though you are increasing the voltage. You can see R is very high. And here you can see the R is low. Especially in this part, because small increase in voltage, big increase in current. And remember, it's the opposite, right? So in this question, we have been provided the following table of voltage and current for forward biasing and reverse biasing, and we have to assume the characteristics to be nearly linear, because you can see over here clearly, is the graph linear or non-linear? Is the graph linear or non-linear? It is clearly non-linear. Linear means a straight line. So clearly you can see this curved on this side, same way curved on this side. So definitely this is not a linear graph. And usually this resistance of the diode, you will see capital R, or it will be given as RD. Okay. So we can clearly see that it is a non-linear graph. But it is asking you to assume that over a small range. So if you take a small portion of the graph, like this part, of this part, this part, that small part we can assume to be a line, like we do in calculus and maths also. Basically the slope part, some small part we are taking, we can assume it to be a line. So that is the concept it's saying. And it's saying calculate the forward and reverse bias resistance of this diode. So forward bias, let's do the first part. So we'll do the first part, which is the forward biasing. Forward, let me do in green color. So bias, the resistance formula is simple, delta V by delta I, that's all. So nothing difficult. So we can call this R for the forward bias. Will be change in voltage by change in current. Guys, what is the change in voltage? Take a look here. So it is changing from 2 to 2.4 volts. So change in voltage is 2.4 minus 2. What is the change in current, guys? 80 minus 60 don't do. Look at the milliamp. Unit is important. So 80 minus 60. This is volt. This is milliampere. So will you guys agree with me that the numerator will be 0.4 volts and this is going to be 20 times 10 to the power minus 3 amp. Correct? So basically 400 by 20. So I think we are getting this as 20 ohms. The resistance of the forward bias is 20 ohms. Got it, all of you? Next, let's look at the reverse bias resistance. Reverse bias. Okay. So we'll take a look at the resistance of the reverse bias RB. Once again is delta V by delta I. Now you look at the second table. Now you look at the second table. So again you can do this minus this or that minus that, doesn't matter, but take the same pair. Okay, take the same pair. So let's say do minus 2 minus 0 divided by minus 0.25 minus 0, and note the units carefully, volts and microampere. Micro means 10 to the power minus 6. So in the numerator, guys, we clearly have 2 volts, and in the denominator we have minus 2 volts and minus 0.25 times 10 to the power minus 6 ampere. So that will go on top in the numerator. So finally tell me how much will you get? 2 times 10 to the power 6 by 0.25, okay, which is basically 8 times 10 to the power 6 ohms. So clearly, guys, are you seeing the functionality of the diode? So low resistance on the forward side, 20 ohms, right? And such a high resistance on the reverse side. This is the beauty of diode. That's why it is a conductor on the forward biasing case, and it acts like a insulator, right, on the reverse biasing case. So very, very important concept. Next, please try this question. The VI characteristics of a silicon diode is given in the figure. Calculate the resistance in forward bias at plus 2 volts and plus 1 volts, and reverse bias at minus 1 volts and minus 2 volts. Try this out. So it is saying find the resistance. It is saying find the resistance in the forward bias case at plus 2 volts and plus 1 volt. Okay. So first let's look at the plus 2 volt case. So that means we'll go to the 2 volts, and they have already given us the region. Can you see? They have given us the region over there. We have to look at the change in voltage over here, the delta V here, and the change in current. So for the first case, which is the forward bias, will be the delta V by delta I. Do you guys agree? Delta V by delta I. And suppose when we read the graph, we see that this is 2.2 volts, this is 1.8 volts. This is 2.2 volts, this is 1.8 volts. So what will the values be over here? So plug it in. 2.2 minus 1.8 volts divided by this change in current. What is the change in current? 80 minus 60, but that is in milliampere. So in the numerator, we are having 0.4 volts, and in the denominator we are having 20 milliamp, which means 20 times 10 to the power minus 3. Basically we are getting 20 ohms. Are you guys getting 20 ohms? Yes or no? Tell me. So basically what did we do here? We took this point and we looked in its neighborhood, right? The change in voltage around it, the change in current around it, substituted, and we got the values. Same thing, guys, you can do at 1 volts. Same thing all of you can do at plus 1 volt for this point. So suppose I tell you guys this is 1.2 and this is 0.8. Same thing, guys, you can do for me, and you have been given the currents also. So why don't you try this? You can try this one as your homework question and let me know in the comments. What will be the forward bias at plus 1 volt? Again, do the same thing, delta V by delta I. So try it as a homework question, simple one. You can do it and let me know your answers in the comments. Now for part B, in reverse bias, what will we do? The same thing. Reverse bias concept, we'll do the same thing. So they have asked us at minus 1 volt and minus 2 volt. Now the problem here is it's hard to read the values, right? So what do we do? So first let's try. Let's say this is 0.5, so this is half of it, this part. This is 0.25, half the current, okay. So we are basically looking at this point. So in the reverse bias case, we can see the resistance in the reverse bias will be again same, delta V by delta I. Don't forget that. Change in voltage by change in current. And here what is the change in voltage? What is the change in voltage here? So minus 2 to 0, minus 2 to 0. And what is the change in current? See, current is also having a negative direction, because remember current has a direction over here, positive, negative. So these are negative values, right? Which means opposite to that positive current. So and here at minus 2 volts, it is 0.25. So minus 0.25. And this is given in microamperes, so be careful of that. Minus 0. So basically what I am doing over here, I am taking 2 points, this point and this point. Are you getting? And basically what you have to do, final voltage minus initial voltage by final current minus initial current. That is the meaning here. So delta V by delta I basically means what? Final voltage minus initial voltage, final current minus initial current. Final voltage you can see. So if you want to make it easy, you can put the points over here. So which point we are talking about? This is minus 2, 0.25. And I am looking at this other point 0, 0. So you can be clear by marking it in the graph. So minus 2 minus 0, minus 0.25 minus 0. And this is microampere, this is in volts. So what will you get? Minus 2, so minus minus will cancel. 2 by 0.25 times 10 to the power minus 6. So many ohms. So if you calculate that, how much are you getting? I think you will get 8 times 10 to the power 6 ohms. That is the resistance in reverse bias. Okay, that is the resistance in reverse bias. Now this is a very interesting question, because you will say, sir, what about the resistance in at minus 1 volt? Here we could do it, but at minus 1, how much will it be? It's very hard to read those small values, right? How much will that be? So there you can again, if the graph is given clearly, again you can do the same thing, minus 1, minus 0 and read the current, or you can say it is approximately this high value, right? Because it's 10 to the power 6. It doesn't matter if it's 7 times 10 to the power 6 or 7.5 or 8, right? So you could approximate it, right? But ideally you will calculate from the graph. Okay. So for the second case, so this was at minus 2 volts, and we can say resistance at minus 1 volt is also approximately the same. So this approximation you could do. Important point. So if they give you any of these graphs, change in voltage by change in current, so how do you find the delta V by delta I? As I explained you, important thing is take 2 points. Take 2 points, do final minus initial, right? And same for the denominator also, final value minus initial value. That's it. So you have seen that this PN junction, which acts as a diode, is basically the device which allows current in one direction and doesn't allow in the other direction. So you say, what's the big deal? What's its utility? One famous utility is the half-wave rectifier. What do you have in the half-wave rectifier? Let's discuss it. Okay, very interesting. So suppose your input voltage is alternating. Remember, we have talked about alternating current, where current keeps switching its direction, right? So suppose your input voltage is alternating. So this is an AC voltage, which I represent like this. So my input voltage is alternating, okay? And now I want to get from it, alternating current or alternating voltage means current is in both directions. It flows one cycle this way, one cycle this way. So flows in both directions, yes or no? But what do we want? Suppose we want to convert that AC into DC. AC voltage into DC, or you can say AC current into DC current. Then let's take a look what we will do. Is the goal clear here? So on this side you have an input voltage. This side what you have? This is basically a transformer. Right? This is what you have seen. This is the representation of a transformer, which is basically either decreasing your voltage depending on whether it's a step down or step up transformer. So this is basically your transformer. Now if you simply connected the resistance to it, or the load, right, what we say the load to it, the output side, it would have current in both directions. But now instead of doing that, if let's say I put a diode and then a resistance. Now let's look at it. What is the interesting thing that's going to happen? It's very interesting. Okay. So first half cycle you will see that this part is positive and this part is negative. Clear? First half cycle, this part is positive, this part is negative. So as a result on this transformer, this is the primary coil, this is the secondary coil. This part will be positive, this will be negative. Right? Whatever the voltage. This is the positive side, this is the negative side. Now if you look at the diode carefully, the positive is connected to the P side, the negative is connected to the N side. So will you guys agree with me that this will allow the flow of current? The resistance will show some resistance, but diode will, so it will effectively allow the flow of current. Yes? Do you guys agree? So basically the current will flow this way. So for this half cycle, where positive is on this side and negative on this side, current will beautifully flow this way. But now let's say This is an alternating current. So in the next half cycle, what is going to happen? Tell me. In the next half cycle, what is going to happen? So in the first half cycle, the current flows this way. Okay? Because remember, our voltage is like this, right? It is an alternating voltage. So if I show this as the input, so this is the voltage on the input side or current on the input side. So this is the alternating voltage. So in the next half cycle, the voltage will become negative, which means this plus minus will change to minus plus the next time. So second time, maybe this one I'll draw it in blue color, this current. In the next half cycle, it's going to be the opposite. This one will change to positive, this one will change to negative, right? So this side will become positive, this side will become negative. Now look at the yellow colors. This side positive, this side negative. That means the diode is reverse biased. The first time the diode was forward biased. It was forward biasing. This time it is reverse biasing. So when there is reverse biasing, there will hardly be any current, right? So here the current will be approximately 0 for the second half cycle. Or you can say the voltage will be approximately 0. Same thing, voltage or current. So on the output side, what will we see? What will we see on the output side? That on the output side, for half cycle, we are seeing the same voltage or a current, which is basically divided by the resistance. In the second half cycle, in the negative cycle, we are not seeing the voltage. Again, next time we are seeing it. And in the second time, we are not seeing. So basically, you can see what is happening here in the positive cycle. So in these positive cycles, when the voltage is positive, we are seeing that the diode will allow it, there will be forward biasing, so it will allow the current, and there will be voltage, the same voltage will be seen on this side. So here, basically what is the graph I have drawn? I have basically drawn a input voltage versus the output voltage. Input versus the output. Or you can also think it to be current, just divide by the resistance. So can you see that only half of the AC current is coming out, or the AC voltage is coming out. That is why it is called half wave rectifier. So its goal is to convert the alternating voltage into DC voltage. Okay, its goal is to convert the alternating voltage into DC voltage. We want it only to be, so basically you are doing a AC to DC conversion. Can you see here? So can you guys see that? We are doing a AC to DC conversion, but only half of it. So actually you are wasting half of the energy. So that's a big energy loss, or little more also there will be some losses. So it will be less than 50%. The output of your half wave rectifier. Here there is no voltage, zero voltage or zero current. Here there is positive voltage or current. Make sense? Now let's see that how can we fix this, because we don't want to be energy wasters. Suppose we want to convert all the AC into DC. The goal is clear. We want to convert the input voltage. It should not flow in both directions. Rather than both directions, we want to convert it into one direction, into DC, but we don't want this half thing wasted. So here very interesting thing is that we will not use just one diode, we will use two diodes. So let's see the very interesting connection here. So in your full wave rectifier, which looks something like this, so here is your alternating, your input. So this is your input AC voltage, okay, and then this is your transformer, and now instead of one diode, you have two diodes, and you sort of center tap the load. Resistance means the load, the output, where let's say load you can consider your bulb, fan, anything, right? Just a simple example. So this is your resistance, and it is connected by diodes on both sides, and the arrangement is like this. Now how will this magic work? It's very easy, we'll analyze it. Okay, so first half cycle, because remember again the cycle was like this, remember our input voltage was like this, okay, positive negative, right? So it was both positive and negative. So in the first half cycle, what happens? This side is positive, this side is negative. So that means this side is positive, this side is negative. Now look here, again see which direction will the current flow? Which direction will the current flow? If this is positive, this is negative. For this diode, this is connected, positive is connected to the P type, negative is connected to the N type. That means the D1, diode 1 is in forward bias. Yes or no? First time this diode is in forward bias. So therefore the current will flow this way. So therefore your current will flow this way. Correct? What about this diode? Will it also allow the current? No. The negative is connected to the P type. Positive is connected to the N type. Look at the connection carefully. This will allow no current in the first half. Right? In the first half, there is no current. Okay. So we can write over here first half. First half there is current. And here first half, or sorry, we are using the blue color. First half there is current. First half there is approximately no current. Nothing here. Now let's take a look at the second half cycle, which when it becomes negative. So what will happen over here when it becomes negative? So this becomes negative, this becomes positive, which means this becomes negative, this becomes positive. Now look at the story. D1 is in forward bias or reverse bias? Tell me, take a look at the diagram. This negative is connected to the P, the positive is connected to the N. So clearly it is opposite, right? Reverse bias. So this guy in the second half cycle, it is reverse biased. So current here is approximately 0. But this guy is in forward bias because the positive connected to P, negative connected to N. So in the second half cycle, there will be current this way. Now what happens to the resistance? So this, when it allows the current in the first half cycle, where will the current flow? This diode is not allowing. So current is like a river, it's like a water, it wants to flow. So in the first half cycle, look at it. Look carefully now at the diagram. The current will flow in the first half like this. And in the second half, the current will flow like this. So in both the halves, is our load getting current? And it is getting the current in the same direction. That is very important. Because this whole thing about rectifier is, we want to convert the alternating voltage from AC to DC, right? Because now you can see both times, see carefully, the current is in the same direction, or I can say voltage is in the same direction, same thing. Voltage, current doesn't matter, just you have to divide by R. Okay. So what will the output voltage look like here? What will be the output voltage? So the V out, the output voltage is going to look like this. Positive, again positive, again positive, again positive. But the shape will be there. So it's basically these negative sides are flipped to the positive side, right? So the shape, this bumpy shape will still be there. Make sense? So very, very important, you have to remember what is the job of the rectifier? Converting alternating voltage to direct voltage, or alternating current to direct current, which you can clearly see in the graph. Both guys are doing it. This guy is doing half a job, not a full job, or even wasting a little more, right? Here also there will be some loss, right, in the transformer and there, right? But there will basically be some energy losses, but at least this is a full wave rectification. So here you can clearly see alternating voltage or current, here only in one direction, right? So please write this job down. Important point, the whole job of rectifier, both whether half wave or full wave, is to convert from AC to DC. AC to DC. And these are a lot of applications because there are many devices which need direct current. But you know what do we get at our homes? Alternating current. Right? So there are many places where you need a rectifier where you don't want a direct alternating current, you actually want a direct current. So you have to connect a rectifier. Clear? DC motor will require this, right? It cannot tolerate AC current, otherwise it will constantly go like this. Okay, so you will require rectification. So this rectifier has a lot of applications, right? Whether you use it in your, like I told you, the devices which need DC voltage, like your television, or let's say you're charging your phone or your laptop battery, that will need rectification, right? Because charging cannot happen with a alternating thing. Okay, the battery will go crazy. So there you need all this rectifier. Okay. Now let's take a look at an interesting question. this is I think in your NCERT textbooks, a PN junction, right, when forward biased has a drop of 0.5 volts, which is assumed to be independent of the current. Now the current in excess of 10 milliampere through the diode produces a large joule heating which burns the diode. Okay, if we want to use a 1.5 volt battery to forward bias the diode, what should be the value of the resistance used in series so that the maximum current does not exceed 5 milliampere? So basically in diode you cannot have very high current flowing in it. It will spoil the diode. Okay, so here clearly you want to limit your current. You want to limit the current in the diode to 5 milliamp. So basically in series means our picture is going to look like this. This is our PN junction or diode. This is the resistance. What have we been told about the maximum current? Current we have been told should not exceed 5 milliamp. And they have given us that we are going to connect it to a cell, external cell of 1.5 volts. Your job is to find the resistance. What resistance will you use? Okay. And they are saying that when forward biased, there is a drop of 0.5 volts which you assume to be independent of the current. So what is the voltage drop in the diode? That is marked over here for you. 0.5 volts. So come on guys, can you solve R for me? Tell me in the comments. Try it out. Try it out. So it's a very simple question actually, nothing special here, right? Because just like this has a resistance, diode also has a resistance through which there is a voltage drop. So this is 1.5 volts, and what type of connection is this? Clearly you can see it is in series. The same current is flowing through. So if diode is having 5 milliampere current, resistance also has 5 milliampere current. You need to calculate the resistance. If there is 1.5 voltage total here, 0.5 here, so how much voltage here? Clearly 1.5 minus 0.5, 1 volts. So now you can easily calculate this resistance. Resistance is going to be voltage drop by current, which is clearly 1 volt by 5 milliampere. So 5 times 10 to the power minus 3 ampere. Correct? So basically you will get 1000 divided by 5, which is nothing but I think you are getting, tell me in the comments, are you getting this answer? 200 ohms. 1000 by 5. So that's it, simple question. Again showing you that diode also has some voltage drop, right? But it allows small amount of current. That's why we said this is a forward biasing case. In forward biasing, diode current is milliamperes, reverse biasing microamperes. Clear? So hope you guys enjoyed this class on PN junction and diode. So we looked at PN junction, diode, and we also looked at its application, which is your half wave rectifier and full wave rectifier. So I hope these concepts are crystal clear to you, and do check out the courses on our website manochaacademy.com and our Android app Manocha Academy. All the links are given below, and please do share it out with your friends as well. As you know, we have courses on science, maths, coding, AI, and our IIT NEET foundation courses. In our courses, you are going to get live classes, concept videos, quizzes, questions, mock tests, and revision notes. So guys, do check it out, and please make sure you have subscribed to our YouTube channel, follow us on Facebook, Insta, and X. So stay connected with Manocha Academy and just enjoy your learning.